the problem name is count square submatrices with all ones. Given a m cross n matrix of ones and zeros, return how many square submatrices have all ones. So in order to solve this problem, let's take this sample discuss. Right, so in order to solve this problem, let's define dp of I comma j as number of square matrices that can be formed with I minus 1 comma j minus 1. So we are just offsetting the indexes by 1, right? Instead of starting with 0, we'll start from 1 with I minus 1 j minus 1 as the bottom right corner of matrix and 0 comma 0 as the top left corner, right? Uh, so one thing that we can be sure about is if, suppose I comma j, suppose we are at 1 comma 1. So we want to know how many square matrices we can from I minus 1 j minus 1, which will be equal to 0 comma 0 in this input matrix, right? But if this point itself is a 0, then even if we can form some matrices somewhere to the somewhere to the top, somewhere to the left, and somewhere to the diagonal, even then we can't extend those, right? Because this is a 0. So we can say dpij will be equals to 0 if matrix of I minus 1 j minus 1 is 0. But if this is 1, then there's a possibility that we can extend the previous uh, matrices that we can form to up, left, and diagonal. Why these three directions? Suppose this is a 1, right? And we know how many squares of matrices we can form at this point just above. Then, like, we can extend those if, like, we can form, suppose like, let's try to see with this 3 cross 3 square matrix, right? This is a 1, and because we know how many because we know we can form a 2 cross 2 submatrix here. We can form 2 cross 2 submatrix to the left, right? And we can also form 2 cross 2 submatrix to at in the direction of top left diagonal, right? The square submatrix. So that's why we can extend these submatrices in this direction, and we'll be able to form a matrix of plus 1 size, right? We could form 2 cross 2, now we can form 3 cross 3. So that is the only concept that we'll use. So the recurrence relation will be something like this will be equals to minimum of the number of submatrices that we can form above to the left and at the diagonal top left, right? And whatever the minimum is, we can form increase the size by 1. Suppose we can form suppose this minimum value comes out to be 3. Now, like, we need to count how many square submatrices, right? So what contribution will this quantity have to this result that we need to calculate, right? So suppose this quantity comes out to be 3, which it will for this corner, right? So at this corner, if this quantity comes out to be 3, means this is the maximum size of the square matrix that we can form. So let me change this definition. This is actually the max size, right, of square matrix that we can form, right? So if we can form 3 cross 3, then it implicitly implies that we can easily form 2 cross 2, and we can also easily form 1 cross 1, right? Just starting and ending here. So basically, whatever this quantity is, we just need to add this to whatever result variable we'll be maintaining. And in the end, we'll get the answer. So let's do the dry run for this sample discuss. So result is currently 0. So this is what we'll return in the end. So at this, we'll start iterating using these in this normal direction, left to right and top to bottom. So this is a 0, so we don't need to calculate any contribution for this point. This is 1 to the up. There's no point above, so we can assume it to be 0. There's a point to the left, but it is 0 in the DP, so we'll also maintain this DP, right? So everything will be 0 in the beginning. So this is a 0, so we don't need to change this. This is a 1. There's nothing above. There's 0 to the left, and there's nothing to the diagonal, right? So minimum of all, like if there's nothing, we can assume it to be 0. So minimum of 0, comma 0, comma 0 is obviously 0. So we can form whatever this minimum is plus 1, because this is a 1. So maximum size we can reach with this as the bottom right corner is 1. Similarly, we can there's nothing to the above. There's nothing above 0. 1 to the left. Sorry, 1 to the left, and there's nothing to the top right, top left. So 0 will be the minimum value of all these three, and this will come out to be 1. Similarly, this will come out to be 1. Now we come to this. This will remain 1. Minimum of 1, comma 1, comma 0. This will be 1. This will be 2. This will be 2, right? Minimum of 1, 2, and 1. Now this will be 1. This will be 2. This will be 3. Now let's sum all these values up. So result will be equals to 1 plus uh, 1 plus 1 plus 1 3 plus 2 5 plus 4 9 plus 3 12 plus 3 15, right? So which is what is returned in the end. So let's code this approach up. So before defining the DP matrix, we can say length of matrix is n, which is the number of rows, and n will be length of the first column, first row, sorry. So this will be equals to, basically we just need to fill this with zeros, right? Let's start iterating from 1 to m. And we can say if matrix of I minus 1, because we have offset by 1, right? All the indexes. this is 1, then we can say left is equals to dp of I minus I j minus 1 up is equals to dp of I minus 1 j, right? And diagonal is equals to dp of I minus 1 j minus 1. It doesn't matter if we can, like, if L is greater than U, suppose L is 5, U is 3, DD is 3, right? Doesn't matter if we can extend much more in one direction because a square is of uniform size in all the directions, right? So that's why we just need to take the minimum. So we can say dp of ij, this will be equals to minimum of left, right, no, not right, up, and diagonal plus 1. And we can say result, which I can just define it here, and we can return it in the end, right? And we can just say plus equals to dp of ij, which we just calculated. So let's try to run this code now. Okay, I think this will go till n plus 1, where, like we are offset by 1. So as you can see, we are passing the sample test cases. So let's try to submit the solution now. As you can see, we have passed all the test cases. So thanks for watching.